Good evening, everyone. My name is Srinivasan, and my here is Zahir. This presentation is going to be a two-part presentation. I'll be presenting the first half, and Zahir will take over in the middle. And the title, Happy Feet, Recognizing and Assessing Dance on the Floor. This is the title of the paper. We see that in the recent times that IoT devices have been finding a lot of applications in various fields. So we sought to find a different application in a classroom setting where a classroom setting of a dance class where a lot of people would dance. We would like to detect the activities that everyone dances and give some sort of a feedback to the instructor so that the instructor can focus on fixing the problems of the student learners. And we also wanted to use such IoT devices to create a smart environment where we can learn complex activities. So dance is a form of a complex activity. The reason is that, as you can see here, we have listed few daily activities, instrumental daily activities as well. These activities are considered much simpler because a lot of researchers before have successfully tried to detect these activities with even a single sensor. However, on the other hand, you can see here that dance activities which involve subtle rhythmic movements of limbs and different body parts. These are really highly choreographed and they have to be performed really precise. So this makes dance activities much more complex. Here we showcase some of the classroom setting that we are targeting. As you can see here, there are a high number of participants in these classroom settings, and we would like to highlight some of the mistakes that was performed. As you can see in the second figure, the two ladies over there performed the same activity at the same time, but in two different ways. And over in the third figure, you see that a person is completely dancing in the the mirror in the middle of it, right? So we want to mitigate these kind of errors. We want to let the instructor know that people are performing wrong steps. Actually, here the instructors are more concentrated on showing how to perform the step rather than fixing the problems of the student learners. One might say that cameras can be used to detect such activities, but there are a number of challenges with that. One camera cannot, or it is difficult for to use a single camera to detect the activities of so many people, especially when there's a big dance routine which involves dancing in circles. The camera tends to lose the track of which person is where and mix up the data. So one way of solving this problem is to use multiple cameras, but then it's going to be expensive both cost-wise and computation-wise. So looking at some popular existing technologies, the first two is called Dance Revolution. It's very popular in Asia. And the third figure is it's basically a Kinect-based app which is called Dance Central. So these are the existing technologies, commercial technologies basically, but then these are not designed for classroom environments, right? And these are like really heavyweight systems. These are not portable, so we want to make a portable system that can just take the devices and go somewhere else and start dancing. It's going to recover data. We want to create such a system. And there have been a few other researchers who have been working in a similar field, but they have been concentrating on collecting data and to detect if that dance is of a particular style, but not finding the micro level dance steps as we are trying to do here. So we have few expectations from a dance activity recognition system. So our system, we expect it to capture dance activities with greater details. We want to use inexpensive sensors. We want it to be portable, lightweight, and we also want it to provide a real-time feedback to the instructor about the performance. So in this paper, we have concentrated on the first two part, and the third point is we have left that for the future work. So in order to develop such a system, we asked ourselves a few questions, like why do we need multiple sensors? As I said earlier, dance activities are much more complex. Even then, is one sensor enough to capture all the activities, or do we need 4 sensors, or do we need as many sensors as this gentleman is wearing here? So this was the main question that we had to answer. The second is how to select a sensor. Do we need an accelerometer sensor, or do we need a camera? Do we need both of them together? Do we need a blue one or a red one? We have to decide that. And then once we have the sensors selected, we had to decide on how much data we want to train a good model. And then as dance involves a sequence of activities, we had to break it down into smaller micro-level dance steps. And the data has to be labeled because we are using supervised machine learning approaches. Right, so we have to design on what granularity we should go to label the data. And then which algorithm do we need to detect such small micro-level activities? And finally, a method to evaluate and assess the model. In an attempt to address most of the questions listed before, we propose HappyFeet. It is a body sensor network of 4 accelerometer sensors, one on the 4 limbs of the body. We then get the signals from the 4 sensors, but then we found that the signals were not synchronized. So in order to synchronize them, we made the participants jump twice before the collection of the data. So we found the patterns of the jumping and we synchronized the signals which we got from all the 4 sensors. And we also took a video recording of the entire dance routine, and we also matched the video with the sensor data based on the jumpings. Once we did that, we had to annotate the data, label the data. So for that, we used a software called ELAN, which is basically a video annotation software. But since we had synchronized both the video and the sensor data stream, we had to annotate the video, and we exactly knew the start and the end point of each and every activity. We'll be showing further that the activities are like really small, so it was a challenge to annotate the data. And once we have the labeled data, we fed that to both shallow learning and deep learning models. So in order to select sensors, we wanted to use easily available off-the-shelf sensors. So we picked a few sensors which are available easily, and we chose Actigraph for our experiment here based on the listed selection criteria. And as far as the dataset is concerned, we had 10 different dance steps. It was collected from one professional dancer and 4 beginner students. And the dance style that we chose is Manipuri dance, which is an Indian classical dance. We chose this dance for a reason, because this dance involves really subtle and smooth transitions. This do not have a really, drastic movements and all that. It was very gracious. That's the reason we chose this dance style. As we can see here, the first video has 3 dance steps as listed below. We could not find a proper name for these dance steps from the literature, so we had to make it up. Even though it says both wave both hands, when they were waving both the hands, there were few movements of the body and the foot as well. And as you can see in the 3rd and 4th videos, there's even room for breaking down the dance step even further. But for this study, we just stuck to these 10 different dance steps. Zahir is going to take over now.
Thank you, Srini. My colleague already explained some of the challenges that we tackled during the annotation phase and the synchronization phase. The other challenge that we actually face is that device heterogeneity. So you might ask, like, why do you need heterogeneity or like different sensors? So if ideally, in a classroom scenario where we want to deploy our system, we cannot force the participants to buy an Actigraph just because they want to do the dances here. So, I mean, they should be allowed to choose their own sensors, like maybe some of them might be comfortable using Microsoft Band or Samsung Gear or something else. So our system, our model needs to be really robust to handle all these different kinds of sensors. But the problem is not all the sensors are created equal. Sensors have different biases associated with them. They have different precision and different kind of susceptibility. So we face some of the problems with working with different sensors. Apart from the criteria we have listed in the previous slide, the other problem that we faced is, say for example, with Microsoft Band, when we put the Microsoft Band on the table, it was still showing us some small activity. So it wasn't, it was giving some activity. For example, with ActiGraph, it wasn't showing any activity. That's like a zero-Z test that we call. So another problem was with Microsoft Band, there was some missing data. I'm not sure if it was the problem with the sensors themselves, but we had like 3-4 sensors, but all of them had the same problem, or the API that we are using to collect the data. So this also showcases the problem that we can face with commodity sensors. So these heterogeneity actually creates a lot of issues if you want to use a developer model that is able to work with different kinds of sensors. So at the end, for this paper, we start with 4 ActiGraph sensors, but in the future we will want to explore the idea of using different sensors. We'll get to the details of that later. So here's a detail of all the data processing steps. So as you can see, for each of the sensors, we ended up with, let's say, about 76,000 data points with windowing approach, and we also made sure that we had a really good training test and validation split. And this split was actually done before the windowing. So the data in the test set and the validation set doesn't have any overlapping with the training set. So we were careful enough to do that. And with shallow learning approach, we use some standard methodology that has been discussed over and over in the literature. So we applied median filter for the movement noise or any other noise that is associated with the sensor, and then we extracted 46 features from them. We did feature selection, and then we tested, a few common machine learning algorithms. We also optimized the hyperparameters in even the regression parameters with the validation set. So we wanted to make sure that our algorithm, the shallow learning algorithms, are performing to their peak performance. And then we compared that performance with that of deep learning method. In this case, this is like convolutional neural network-based methods. So the parameters of the neural network, convolutional neural network are listed here. We tried different combinations. So we started up with like simple one, and then we moved to complex architectures. Here's a much better visualization of the whole architecture of the CNN model. So we tried up to 3 layers, and we up to 2 fully connected layers. And each of the convolution layers actually had like ReLU and an average rule followed by a dropout. So the dropout was added so that our model doesn't overfit. And so here are the results of all the shallow learning methods for individual sensors. And we can clearly see that random forest is performing better compared to other methods that were discussed in the previous slide. So for comparing against like CNS-based models, we start with random forest as a baseline. So our best CNN model that we got from 3 CNN layers and 2 fully connected layers outperforms random forest by 7% on the individual sensors. So, and then, but how, you might ask, how do you say that 3 layers of convolution layers and 2 fully connected layers? I mean, why did you say that? So we actually started with simple, in the column that you can see, we have like 1 CNN layer and 1 fully connected layer, and increasingly we add convolution layers and fully connected layers. And also, because all the sensors are synchronized at the beginning of the data collection, annotation step. So we can actually readily modify our 3-channel accelerometer model to encompass all of the 4 sensors, because effectively that is like 12-channel data, because it's transparent to the CNN network. So on the top we have all sensors combined, and then we compare the train accuracy and the validation accuracy in this whole graph. As you can see that as we keep adding layers, we have increasingly better performance. And this is the figure that we are showing of the test accuracy, and the test is truly held out set, so there's no overlapping with the training. So the conclusion that we got is that fusion of individual sensors and adding more layers increases accuracy over time. But another interesting thing that we noticed is that if we combine all of the sensors and treat it as a 12-channel data, we get like even like one CNN layer and one fully connected layer, we get like 93% accuracy right off the bat, and then it doesn't increase that much. So then we think, okay, so if we have more sensors, we don't need to collect that much data, and then we tried random forest on the all of the data combined, and we actually got very similar results. So if we have 4 sensors or even more, we would get like really similar performance with deep neural networks and even with simpler networks. But if we have one sensor, then of course deep neural networks will be able to extract meaningful information in a much efficient way, and that will give you at least 4-7% accuracy that we have observed. So obviously, this is just as you have seen, this is just the first preliminary stages of our work. So there are a lot of limitations. As we talked, we experimented with that, and we shared our story of failure. So we could not actually, integrate the device heterogeneity into this model right at this moment. But we were thinking that because different sensors will have different distribution, what about using a generative model to sample the distribution and convert that to a homogeneous distribution. So if I have Microsoft band and coming from I'm collecting data from Samsung here, but if we can train a network in a way, like for example RBM or generative adversarial networks, to sample the distribution and then have a homogeneous distribution, so that might be helpful. We are not sure. We are just investigating that. Capture finer dance moves. I mean, as Srini has already demonstrated in the previous slides, that there is room for improvement to capture even finer dance move. Obviously, annotation is going to be a problem, and we need to collect even more data and integrate data from more participants. So the data that the result that we are showing is for the one person who is a professional dancer. We actually tried running the model with the beginner students as well, but it failed miserably because the problem is that it's difficult to design a model that will encompass the learning curve. So if I'm starting out right now, I don't know. I mean, I wouldn't be just throwing my hands and legs like that. You train any sophisticated model, it will fail. But over time, that person will learn, and then the model might be able to recognize that better. But we haven't been able to integrate that. We first wanted to focus on creating a model that is able to capture all of the finer movements. Now that we have proved that a computational method, now we can focus on the other problems. We want to have a better scoring criteria and provide feedback to the users. And also the automation, the annotation is already offline. But I mean that would not be helpful if we want to have it in a downstream scenario. So we want to automate that process. Maybe a semi-supervised or change product detection-based method might be helpful. Integrating the accelerometer-based system with the vision-based system might also be a good idea to try. We might also try other CNN methods, other deep learning methods like LSTM or RNN. And at the end, our system needs to be helpful. So it's not good enough that if we just come up with really sophisticated models, but if the users find it really confusing to use, so we need to evaluate that as well. So at the end, we want to deploy our system in a scenario like this, where children are dancing, and then we can provide some feedbacks. So thank you for listening, and we will hope you have some questions.